If someone asks me what keeps me up at night, it's when you plug in this and does it work or not, really. Great leading conversation to what this paper was about, and I want to thank Ross and Amber for giving us a chance to present it. So my name's Steve Wells. I'm a fellow over at Micron in the Solutions Architecture team, and I'm also presenting with my colleague Suresh Rajgopal, who's a distinguished engineer and has been spending a lot of energy and focus on power optimizations. And you heard from the prior conversations earlier a comment that we're just starting to roll out Gen 5 and Gen 6 feels really far away. That's probably exactly correct from their vantage point. However, as a storage developer, storage controller developer, Gen 5 is in the rearview mirror. All of our energy's on getting Gen 6 figured out right now. Would we want to go less than Gen 6x4? Yeah, there's probably a lot of arguments why that makes sense, but they did say, well, but we still need to make sure it's 4 lanes so it's backwards compatible. And who isn't going to drop the gauntlet and just offer Gen 6 full performance by 4? So we've got to take a look at this and decide what we want to do about this. And what became interesting, this data that I'm about ready to show you, matches the data that was presented both by Zane at Intel yesterday, which was showing performance per generation improvement and power efficiency generation per generation. And then Broadcom also discussed it from networking. Same seems to be true here. We were trying to figure out how to best describe this thing. But we're using random reads as the example in this case. The trends show similarly and other things. If you just kind of look at industry trends from Gen 3 to Gen 4 to Gen 5 and kind of maybe drawing a line to Gen 6, every single generation is improving its power efficiency. So to assume whatever power efficiency that you could measure today is going to be tomorrow's power efficiency is probably incorrect. Looking at this data, it pretty much suggests that every time we transition to a new PCI generation, we typically take a litho conversion that offers some additional performance improvement. NAND continues to optimize its energy per bit to program and erase, and they converge together. But there's also a desire for double the bandwidth in there. And so we kind of look at this and go, well, Gen 5 drives are probably going to be 20 to 25 watts, but Gen 6 is probably going to cross that mythical 25 watt level and could be in a sustained way 35 to 40 watts, certainly greater than 25. So what's interesting about that is okay, the guys seem to be embracing that there's going to be higher energy density in the CPUs or the networking for the additional performance you get, and they will continue to have their power efficiency trends. But there's this interesting thing that informatively EDSFF calls out. Informatively, E1 and E3, E3S1T have a maximum of 25 watts. So do we just abandon these form factors when we go to Gen 6? Are there opportunities to do something else? And that was kind of what we wanted to go investigate and look at. And to give the quick punchline out of it is I think there's a real opportunity within existing standards that we have today to mitigate and continue to stay on the form factor of choice and still offer benefits that you can get from Gen 6x4. And we're going to talk about that, socialize it, see what we get. So 2 things. Where does 25 watts come from? Well, first of all, this is a first snippet of the OCP data spec, which discusses something called max average power. So max average power, we believe, is a thermally relevant power. It's 2 millisecond sampling, 1 second averaging. And then there's a peak power, and peak power is a much finer sampling window. That's so arguably we say max average is good for thermal discussions. Peak powers is good for regulator discussions. And it also says that max average defines the measurement methodology that would be used for setting power states. So informatively, SFFTA, and I have a quick snippet out of the E3 one, and again, admittedly, they call it out informatively. They call out 25 watts for E3S 1T, 40 watts for 2T, E3L 40 watts, and 70 watts for E3L 2T. Interesting question, and I've been asking around, and if anybody has a better answer, I'd like to hear it. Where did 25 watts even come from? Why did the line get drawn at 25 watts? And the best history that I can figure out, it came from the chem connector originally, and it was really a discussion of amps per pin. And then it moved to the 8639 connector used in U.2, and it was also an amps per pin discussion, and somehow that turned into a thermal thing. And power for electricals versus power for thermals are not the same thing. Confusing them can get you in trouble. You're typically going to have more amps per pin and peaks than you do in your thermal averages. And if you try to equate them, you can leave margin out there. On that, pass it on to Suresh.
Thanks, Steve. So Steve talked about max average power measured at 1 second averages as being thermally relevant. So what we wanted to see was, how fast does temperature change? And we looked at two form factors here. You can see the E1S, this is a smaller form factor, 15 millimeter, and then the larger E3S2T. They're both assume there's no throttling. These are two drives running the same workload, same power, airflow and temperatures are identical on both configs. And the thing to notice is not the peak on this or the top of the graphs, but really the gradient that you see here, which represents essentially the thermal mass or thermal resistance associated with how quickly does the temperature get to the next level in that 1 second. And you can see for a 15 millimeter E1S, it's about half to 0.75 degrees per second. The E3S2T, on the other hand, is less than a quarter degree per second from going from an idle to an active workload. So the takeaway being, depending on the form factor and, of course, your system airflow capabilities, the gradient is anywhere between a quarter degree to a degree centigrade per second. Okay, so now that you're there, everything we're talking about as we go into trying to find a way to operate at that, burst performance level, to step back, we start with just looking at how throttling would typically operate in an SSD. And what you see here is kind of a high-level flow chart of operations inside an SSD. On the top, you see host traffic coming in. Typically, these are reads or writes that need to take place on the NAND. As it gets into the back end, you've got what we've heard a lot about is garbage collection. Refresh operations would generate additional operations into the NAND. So now you've come into the back end, and you've got a certain amount of NAND operations you want to perform. They require a certain amount of power. So the question is, how much power do you have? And so the power that you have is typically defined by an NVMe power state setting. So that tells you, okay, you're set at 25 watts, or 40 watts, or 20 watts. That tells you how much power you have. On top of that, you've got a temperature derating that tends to get applied because your drive is constantly monitoring through its temperature sensors what is the composite SSD temperature that the drive can operate at. And that tends to apply a derating factor to your allowed power. And finally, that comes into your allowed power, and you determine how much power you have versus how much power you need. If you've got sufficient amount of power, you go off and execute the operations. If you don't, that's when you go off and throttle to some extent. Now, when you throttle, throttling you typically are stalling, and that's going to introduce some form of latency. And we'll talk a little bit more about the latencies as we go in, as we look at these two options. So as far as options to consider, to keep the thermals under the 25 watts, obviously lane reduction is one option, but you're going to compromise performance that way. You could set your NVMe power state 0 to 25 watts for the form factor, which is the recommended number, but then you're going to throttle anything above that. The third option would be to do some burst with thermal throttling. And the thing to keep in mind here is when you do those bursts, your latency is going to change. And the graph on the left essentially shows you a plot of latency over time and the sort of a 1 minus CDF, or sort of a failure plot of the 9's from the top to bottom. And you'll see that the green, which is your power state 0, is showing a trend towards an increasing latency. Once you get to a lower power state, as soon as you get to a lower power state, now as you looked at it in the previous graph, you've got that throttling effect happening, and you're introducing latencies. So the challenge here is, how do you manage latencies while continuing to deliver performance at the capability of your, say in this case, Gen6x4 interface? And so I'll hand it off to Steve.
So I think you guys are potentially getting the idea that we're considering here, which is to what Suresh showed on the last slide. You can also see it here. If we have a no throttling situation, we have a latency profile that's better than a throttling situation, which I'm trying to highlight here with my cursor over in here. And if we're just going to just draw a line at 25 watts, and then you'll always get these increased latencies. And the question is, well, maybe why should you? If your temperature is, your composite temperature is reporting meaningful margin to worst case temperatures, and yet you're going to continue to just throttle it because 25 watts is what the informative direction is, or what the thermal sustainable is, you're leaving an opportunity to reduce the latencies over time here. There's two ways to do this, and we tried to show this pictorially. This is a bit of a cartoon here, but as you start running a drive, let's say would be no throttling down here, we start driving up and the power starts getting high. I'm sorry, the temperature starts getting high. Well, at some point in time, you're probably going to have to potentially have the host issue a reduced power state. As you issue the reduced power state, the temperature will start to fall, and there's no reason why you couldn't allow it to go back and burst into the higher power state, and then you end up with this kind of sawtooth, or sometimes, as I describe it, whiplash. And you would transition from one latency distribution profile to another latency distribution profile, and it would bounce back and forth. And this is perfectly feasible, perfectly viable. Either a BMC could be involved in doing this, or the host software could be involved in doing this by just issuing the DSSD power state commands, or the NVMe power state commands to get this job done. There is another option, and this is also actually in the NVMe spec itself, which is called host-controlled thermal throttling, or thermal management. And in this case, what you do is you specify a temperature called TMT1, where you begin to throttle, and a TMT2, where you have a full throttle situation. So in this particular cartoon example here, I said, well, let's start throttling at 65 centigrade, and I want to be fully throttled by 75 centigrade. And what ultimately happened is, as it began, there was no throttling, and then as it starts recognizing there's more and more closer to past 65 TMT1, it starts increasing the throttle rates more and more. You end up seeing kind of a throttle level that picks a number that kind of works out to the average of what the sawtooth pattern might look like. But ultimately, you end up with a stabilized latency distribution as one benefit of merit to this. The second benefit of merit to this thing is you're not taking the thermal cycling, which could be, as we mentioned, half degree per second up to, or a quarter to maybe a full degree per second, just having this oscillation of the thermal temperature and the thermal stress on that. So the answer continues to be throttle only when thermally necessary, just allows burst workload upside. And this offers, we believe, a better solution in either state, either way, either host managed or the host managed power states where the drive is being fired new power states, or just let the drive go figure it out and just give it guidance on when do you want to start throttling and when you want to be fully throttled, and it will pick up the details. So in conclusion, power efficiency improvements are just not keeping up performance per generation. So Yes, we are getting power efficiency improvements. They will continue to go, but if the trends follow as they may, it's still going to be the point where we're going to end up with a greater than 25 watts situation here. So we could either just never let that happen and just accept the additional latencies, or give an opportunity for a burst upside. And supporting power states based on the mechanical thermal limit allows just reduced throttling residency. And again, throttling residency can come from either the workload itself and power throttling, or come from thermal throttling. You know, throttling residency is throttling residency, and throttling residency is going to increase the latencies. But the goal here would be to just, let's only throttle when thermally necessary, not just throttle on some math on worst case form factor. So to do this, supporting power states above 25 watts, even if you have a drive that offers a 25 watt form factor, such as an E1S, offer power states above 25 watts. This would give the host an opportunity to work with this. Also allows host-controlled thermal management to do its thing. And either option is available to mitigate against getting thermally too hot within the workload. I think there's also an assertion coming up that not many workloads are in that thermally sustainable spot. Admittedly, we always do all of our benchmarking against sustained random reads, random writes, sequential reads, sequential writes. The reality is real workloads probably have less full pressure residency, and as such, then I think you're leaving opportunity on the table if you just lock the power at say 25 watts. Call to action then. So for the storage vendors, support power states above that thermally sustainable TDP for a particular form factor. That doesn't mean you can't ship a default power state of 25 watts. For those form factors, but give the host an opportunity to consider working with that. And then support the host-controlled thermal management aligned to the data center specification, but allow the way the data center specification today is set up is it's really, the best way to describe it, it's drive-on fire thermal throttling. And if we have the host-controlled thermal management with the host allowing to issue revised thermal throttling parameters, this can help. And then as a host side, evaluate the progressive host-controlled thermal management solution. I'm sorry, on the drive side, evaluate progressive host-controlled thermal management. Many drives just go from no throttling to lots of thermal throttling. And to the picture that we showed in here, there's no reason why we can't have some sort of linear degradation with temperature, as opposed to just a simple 1 or 2 point step function for thermal throttling. And there are drives out there today that are doing that. And then on the host side is, for the host and the vendor side, is just collaborate with the OpenBMC project where some of this is happening, and maybe there's an opportunity to get some of these concepts in there. And then I think some of the OCP projects supporting burst power are useful. And I think I'd love to continue this conversation in the storage work group and get some feedback on this and see where this goes. That's all we had. Comments, questions, and as other presenters have said, I see nothing. Thank you, Mr. Lee.
So I like where you're going here. This is super interesting to me. But one of the things I was looking at, trying to understand in my head. So today we have kind of the 70-degree point and the 77-degree point. It's kind of being, I'm starting to get warm, and then at 77, it's like now you're going to start throttling in OCP, right?
That's how it's defined today, yes.
And in that regime, that's really a hint to the BMC to what it's going to do with the fan RPM, right? So that's where it's going to try and give you more to cool you off. So it's how do you kind of pick the points for this to start that throttling ramp versus where I don't want to cut short my efficacy of that fan ramp and leave myself some stuff on the table for that latency.
It is a legitimate concern, right? You have multiple stable feedback loops that are now in the same space, and then those multiple feedback loops can interact potentially in unacceptable ways. And you're right, the way the OCP spec was envisioned is the BMC is monitoring a bunch of different temperatures around the system, including the SSD, and then making a decision to crank the fan speeds, and there's a latency associated with that, and as Suresh pointed out, it could be maybe a degree per second of thermal rise, so it might take a while for those fans to ramp up and work on that. It's a good question. I think there's going to potentially be some opportunity to collaborate in there. Today, by the way, we have this exact implementation in our Micron SSDs where we just ultimately set our TMT1 to 77 and set the TMT2 above that. And then, that ultimately gives a higher temp, but that may be okay even at those levels if we wanted to keep those levels. In this particular example, I actually set TMT1 down to about 65, and it just felt like, well, with our goal of trying to hit, and even OCP spec says that, our goal is to kind of line and land as close to 70 degrees as possible. This particular example, I think with the TMT1 at 65, it landed around, 71, 72. But yeah, I think there'd be some exploratory work around that. I'd definitely advising to follow the OCP spec to deliver this and just make sure TMT1 is set to 77 and TMT2 is set to the bigger figure. And I don't know if that's called out in OCP or not. Maybe you can let me know. I think it's around 85 or 80 for the 85 for the high-end temperature. Yeah, so that's, we can keep those. But if a host wants to just redial those down, as long as the drive honors, allowing to set a new TMT1 and 2, we could lower that down, potentially get an alignment that works better. And there may be some exploratory work that would need to be done with the host system and the BMC to see if we got the feedback points right.
System characterization here is fully warranted. So.
But end result is speaking strictly from sustainability, it's hurry up and get idle. And throttling to 25 watts just slows you down to get idle. And that's where, so, if we got the thermal margin, let it get idle sooner. And it just overall reduces the energy consumption and ups the power efficiency if it's supportable.
Yeah, Steve?
Okay.
So another feedback mechanism
Hey,
which
John.
we're going to have to figure out is L0P.
Yes.
Which allows the host or the device to downshift the number of active lanes without stalling. Without stalling is a huge advantage over your start-stop stuff that you're talking about here. That only applies to PCIe Gen 5 and above, but it's something that we have to add in as yet another feedback loop as to how to do that stuff. And that will also be under host control.
Agreed. And
or device control.
Or device control. That is correct. Suresh, you have anything? Did you want to add on that? Or?
Yeah, I think L0P being a link state control, as long as that is cooperatively enabled between the host and the device, you can certainly take advantage of that. Yes.
Right. And that should help because, not stalling is a big advantage to the system side. This is a very device-oriented point of view.
That is true.
I mean, ideally, we'd love to. Ideally, we'd love to never thermal throttle.
Agreed. Yeah.
If you guys could just fix that at the host level, we'd all appreciate that at the drive level.
That is yet another difference between SAS SATA and NVMe, PCIe-based NVMe.
To John's point about link state management, L0P is an interesting one, and for those that aren't familiar with it, it allows you to very dynamically set the lane widths based on the pressure of the traffic that you're dealing with, and it also should improve the fuel efficiency, so to speak, of the drive that you're dealing with. There are other opportunities as well. If you do have a certain amount of idle residency, there's other NVMe power states as well that can be considered. So,
I'm not sure how much idle we get in the enterprise.
Thanks, John.
Yeah, just a comment to follow on to what Lee was saying. I think this is something that can interact. Obviously, we'll have to interact some with the host and how it manages. But fan speed control, I envision this. One of the ways I see this working is it's a finer granularity or a smaller time increment because you could go, burst to 27 off of 25, and then it's not really thermally relevant. You don't have to increase fans, so there could be a lot of work that happens here at the drive where you don't have to manage it from fans. And then if you do ramp up the fans, you can still be bursting a little bit even at a higher fan speed too if you're really trying to get the max throughput for a short amount of time.
All right, almost out of time. I'm going to throw just one last comment in here. when it's all said and done, and maybe this is going to be part of the conversation over the next year in OCP storage and other places, as well as maybe at this conference again next year, is it would be good to get some fuel economy, fuel efficiency metrics in place, and just running, 4K, random writes or 4K random reads and measuring IOPS per watt. It's interesting, it's useful, but at the same time, these aren't the workloads the real systems get. So what can we do in terms of measuring power efficiency against some workloads? So maybe we can start a little bit like the EPA does with cars, get a couple bookend workloads, one driving on the freeway and one driving in the city, and start being able to evaluate against some better workloads than just strictly full pressure. It's a little bit like saying, what's my fuel economy when I stomp on the gas trying to go as fast as I can for a speed test on my car. It's just is not how it's used. Anything else, Suresh? No. All right, guys, thank you.